Hello and welcome to the Maths 2 component of the online BSc course on data science. In this video we're going to talk about matrices, as you can see up here. Now matrices, you may have heard of matrices in a completely different context. Namely, there is this movie called The Matrix and its sequels, which you may have seen on one of these movie channels. So that has a much more difficult and intricate plot line, and the use of the matrix there is much more involved. We'll see that in actuality the matrices that we need, matrices is plural for matrix, are much easier, and how they deal with vectors and in linear algebra, which we are studying now. Okay, so in this video we are going to study what is a matrix. We'll study some related terms. We'll study diagonal and scalar matrices. We'll look at the identity matrix. We'll talk about linear equations and matrices. So this is the relationship with linear equations. This is really one of the main reasons why we study matrices. We'll look at the algebra of matrices, so things like the addition of matrices, scalar multiplication, the multiplication of matrices, somewhat special. And then finally, what properties do these matrices have with respect to addition and multiplication. Okay, so let's start with what is a matrix. Okay, so a matrix is really something very easy. It's a rectangular array of numbers arranged in rows and columns. Yeah, so it's like a table. Yeah, very much a rectangular table which you're familiar with. And inside the table in various places you have numbers. Okay, so here's an example. So the example has the numbers 1, 2, 3 and 2, 3, 4 arranged in an array, a rectangular array. So in a table if you want. So this is what is called a 2 by 3 matrix. So the 2 refers to the first, so to how many rows there are in this matrix, and the 3 refers to how many columns there are in this matrix. Okay, so the 2 by 3 is written to the right of this matrix, slightly below it. Okay, so 2 rows and 3 columns. Okay, so in general you may have an m by n matrix. So that means you have m rows in this matrix and n columns in this matrix, and we'll talk about the entries of this matrix. So the ijth entry of this matrix refers to the entry which is in the ith row and the jth column. So there's a unique such entry, and that will be the ijth entry. So let's look at the example that we have here and look at the entries in this matrix. So first of all, this has 2 rows. How do the rows look like? Here's the first row and here's the second row, and it has 3 columns. So here's the first column, the second column, and the third column. Okay, and now suppose I want to ask what is the 1/2th entry of this matrix. So the 1/2th entry of this matrix, so the 1/2th entry of this matrix is, so you look at the first row, so that's the first row over here, and you look at the second column. So that's the first row is 1, 2, 3, and the second column is the 2, 3. So the entry that you have over there is 2. Okay, so I'll encourage you to think about what is the 2/3th entry. So the 2/3th entry of this matrix is, so by now you have probably figured out, you look at the second row and the third column. So this is 4. Okay, so I hope you understand what it means for a matrix to be an m by n matrix. That means it has m rows and n columns, and what it means for an entry to be the ijth entry. Okay, so let's move on and look at some special kinds of matrices. So as we saw, matrices are rectangular arrays of numbers. So a special shape within rectangles is the square, right? So let's talk about square matrices. So a square matrix is a matrix in which the number of rows is the same as the number of columns. So here's an example. So here you have 3 rows and 3 columns. So just to jog your memory, here's the first row, here's the second row, here's the third row, and about the columns, here's the first column, here's the second column, and here's the third column. Okay. So again, just as a test, if you want to ask what is the 2/3 entry of this matrix, so the 2/3 entry of this matrix, so you look at the second row and the third column, so that's 1. Okay, so I hope you're comfortable with the notations. So the ith diagonal entry of a square matrix is the ith entry. Okay, so when you have a square, there is something called the diagonal of the square. Okay, and we look at the ith entry on the diagonal, and that's the ith entry of the matrix. Okay, so the diagonal of the square matrix is the set of diagonal entries. So here's the set of diagonal entries. Okay, and within this is the first diagonal entry. So this is the second diagonal entry, and this is the third diagonal entry. Okay, so the diagonal entries are somewhat special because they occupy the ith position. Okay, so we generally talk about diagonals only for square matrices. Okay, so now some further specializations of these square matrices. So diagonal matrix is one where the only non-zero entries are in the diagonal, everything else is 0. Okay, so such a thing is called a diagonal matrix. Here's an example. So you can see that the diagonal entries here, so that's 1, -3 and 4.2. So the first diagonal entry is 1, the second diagonal entry is -3, and the third diagonal entry is 4.2. So everything else is 0. So this is a diagonal matrix. Okay, so then an even more special case of this is what is called a scalar matrix. So diagonal matrix in which all the entries in the diagonal are the same, have the same value, so it's the same number. So this is called a scalar matrix. Okay, so here's an example. So here you can see that every entry here is -3. So the first entry is -3, the second one is -3, and the third entry is -3. They're all equal. So this is an example of a scalar matrix. Okay, why is this a scalar matrix? So we'll see later that this behaves like -3. Okay, this matrix in our mind we should think of it as -3. Okay, again, just to jog your memory, what is the order of this matrix, meaning what are the number of rows and columns? This is a 3x3 matrix. Okay, and an even more special case is where you have a scalar matrix, but in the diagonal position the entries are all 1. So this is called the identity matrix. This is something very important, and it has a special notation. It's denoted by I. Okay, so this is capital I. Okay, so here's what I is. So this is 1 0 0 0 1 0 and 0 0 1. So again, I'll remind you, this is 3x3. So I'm not saying what the size of the matrix is. So if we are talking about a 4x4 matrix, then that will also be denoted by I, and we'll have 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. So it depends on context as to which I we are referring to. So in the given context, it will be clear what we mean by I, meaning how many rows and columns it has. But however many rows and columns it has, which of course is the same number, the diagonal must consist of ones. Okay, so the only choice is how many rows and columns it has, which will be clear from the context. Okay, so these are the special kinds of matrices we wanted to look at. So now let's look at the use of matrices. Okay, so suppose we have a system of linear equations. So we'll study more about this in a forthcoming video. So you have a set of linear equations. Okay, so what does that mean? That means you have something like this: 3x plus 4y is 5 and 4x plus 6y is 10. Okay, so we can think of this as in terms of matrices. So how is this being done? Again, this will be explained in much more detail in the forthcoming video. So the corresponding matrix is this matrix, which has 2 rows and 3 columns. So I'll emphasize the 3 columns here. So the first 2 columns correspond to the coefficients of x and y. So 3, 4 and 4, 6, that's the part that's coming over here. That is this part. And then the entries that are on the right beyond the equals, that's on the last column. Those are in the last column. Okay. So this middle line is just for our own sake. We don't need to put it. So as a matrix, this is the same matrix as what we have without the line. So this is 3, 4, 5, 4, 6, 10. But we later see that putting that line helps us. Yeah. So for now, this is the corresponding matrix. Okay. So, but we'll see how that line helps us later on. Okay. Okay. So that's how it's related to linear equations. And this is really the main importance of matrices. Okay. So now let's move on to how do we add matrices. Okay. So here's an example. So we'll add matrices by adding corresponding entries. Okay. So the important part here is that when we add two matrices, they must be of the same size. Okay. That means they have the same number of rows and the same number of columns. Both matrices have the same number of rows and both matrices have the same number of columns. So for example, over here, this matrix has 3 rows and 2 columns. This matrix also has 3 rows and 2 columns, and hence we can add this. And the resulting matrix also has 3 rows and 2 columns. Okay. So how do we add this? So the addition, the way it works is we take 1 and add it to 0. So here's 1 and 0. So we add these, and in the 1/1th place we get 1 again. Okay. We take maybe let's look at the 2/2th entry. So we have a 7 and over here we have a -7. So we add these and here we get a 0. Okay. So you add corresponding entries. Okay. So I hope this is clear. So let's look at this in a more formal way. So the sum of two m by n matrices, apologies, this should be matrices. So the sum of two m by n matrices A and B is calculated entry wise. Okay. So corresponding entries are added. That means you look at the ijth entry of A and the ijth entry of B, and then you add those to get the ijth entry of A plus B. Okay, so that's the formula. A plus B ij, that means the ijth entry of A plus B, that's what's in the left. That is the same as the ijth entry of A plus the ijth entry of B. Okay, so maybe one more example. So suppose we have these two matrices. So this is this has 1 row and 3 columns, and this has 1 row and 3 columns. And so the resulting matrix also has 1 row and 3 columns. And how do we add these? We add these entry wise. So for the first entry, that's the 1/1th entry, we have half plus 2, so we get 5 halves. For the second entry, we have -3/4 -3, so we get -15/4. And for the third entry, we have 3 minus 1, which is 2. Okay. So I hope so the addition of matrices is fairly easy. I hope you are getting the hang of this. Okay, so the next thing we want to look at is scalar multiplication. Okay, so how do we multiply a matrix by a number? So to multiply a matrix by a number, we multiply each entry of that matrix by that number. Okay, so here we have 3 times the matrix 1, 2, 3, 4, 5, 6. Okay, so 1, 2, 3 is in the first row, 4, 5, 6 is in the second row. So what do? We do this by multiplying each entry. So this is 3 times 1, 3 times 2, 3 times 3, and then 3 times 4, 3 times 5, and 3 times 6. Bracket complete, and which is exactly what we get as the matrix 3 times 6 times 9, 3, 6, 9 in the first row, and 12, 15, 18 in the second row. Okay, so let's make this formal. So the product of a matrix A with a number C, so this is denoted by C times A, and the ijth entry of the product is C times the ijth entry of A. So C times A ijth entry is C times Aij. Okay, then let's move on to matrix multiplication. So this is really the relatively harder thing to do. So let's look at how to multiply matrices. Okay, so here's an example. So let me explain that example before we see how this equality comes about. So let's explain this 7. Okay, how did I get 7? Okay, so in order to get 7, so 7 is the which entry of this matrix? It's the 1/1th entry of this matrix. Okay, so for the 1/1th entry, I look at the first row of the first matrix, and then I look at the corresponding entries of the first column of the second matrix. Okay, so the first 1 and 2 came from here. Okay, and the second 1 and 3 came from here. Okay, so so what is the sum? This is 1 plus 6, which is indeed 7. So that's how I got that 7. Okay, suppose I want to know what is how did I get this 22? Okay, let's ask for 22. So first let's ask 22 is which position? So 22 is in the 2/2th position. Okay, so in order to get the 2/2th position, I should look at the second row, and then I should look at the second column. Okay, and then I should multiply corresponding entries and add them. Okay, so I get 3 times 2 plus 4 times 4. So this is 6 plus 24. 6 plus 16. Which is indeed 22. So I get 6 plus 16, which is indeed 22. So let's maybe do one more entry. Let's look at the 1/3th entry. Okay, 13. How do I get this entry? So 13 is the 1/3th entry. So for the 1/3th entry, I take the first row, which is 1, 2, and I take the third column, which is 3, 5. Okay, so I get 1 times 3 plus 2 times 5, which is 3 plus 10, which is 13. Okay, so I hope the process is clear of how do we get these entries in this matrix. So I'll encourage you to find the other entries. How do we get 15, 10 and 29? Okay, maybe let's do one more example. So here's another example. So we have the matrix 1, 2, 3, 4 times the matrix 5, 6 in columns, in a single column. Okay, so I want to look at how did we get 17 and 39. So for the 17, what do we do? It's a 1/1th entry. So I look at the first row and I look at the first column. So of course here we have only one column. So we have one and multiply the corresponding entries and add them. Plus 2 times 6. So this is 5 plus 12, which is 17. Okay, so for the 39, what do? I do 3 times 5 plus 4 times 6, which is 15 plus 24. And indeed, this is 39. Okay, so I hope it's clear how we are getting these entries. Okay, so now how do I abstractly define matrix multiplication? So if I have two matrices A and B, how do I multiply them? So note here one of the important parts. Okay, here as in the previous example, the matrix sizes were very important. Okay, so we had a 2 by 2 matrix being multiplied to a 2 by 1 matrix. Okay, so what was important about this? The most important part was that these two things were the same, the 2 here and the 2 here. Okay, so the number of columns in the first matrix must be the same as the number of rows in the second matrix. Okay, so the number of columns, so the number of columns in the first matrix must equal the number of rows in the second matrix. Okay, why do we need that? Otherwise there will be a mismatch. Okay, so here I have a 1 and 2, that's the number of, so how many entries do I have? I have 2 entries here, that's corresponding to the number of columns. And how many entries do I have here? 5 and the 5 and 6, there are 2 entries which corresponds to the number of rows. Okay, if I had one more entry, then I would not know where to multiply it by. Okay, so in order for this to make sense, the number of rows of the first matrix, sorry, the number of columns of the first matrix must be the same as the number of rows of the second matrix. Okay, so let's, with this caveat, let's define matrix multiplication. So here you have two matrices. The first one has size m by n and the second one has size n by p. Then the product has size m by p. So this m is the number of rows of the first matrix and the p is the number of columns of the second matrix. And how do we define the ijth entry of A, B? So for the ijth entry, you look at the ith row of A, look at the corresponding entries of the jth column of B, multiply those and add them up. Okay, so abstractly this is summation k is 1 through n aik times bkj. Okay, so if you find this formula cumbersome, go back to the examples, you will see it exactly matches with what we have done. Okay, now important remark which I want to reiterate, I said this before but I want to reiterate this. The multiplication of matrices A and B is defined only when the number of columns of A is the same as the number of rows of B. Yeah, very important. Yeah, otherwise we don't define multiplication of matrices. Okay, so here's another example. So 1, 2, 3 times the matrix 2, 0.8, 5, 0.7, half minus 2 is 13.5 minus 3.8. Okay, so one row and two columns. Okay, where did I get one row and two columns from? That's because over here, so first of all, is it defined? Can I multiply these at all? Yes, because the number of columns of the first one is the same as the number of rows of the second one. And then in the resulting matrix, what was the size? So this 1 is what came here, and this 2 is what came here. Yeah, so the resulting matrix has size 1 by 2, so one row and two columns. Okay, and now how do we get the first entry? So to get the first entry, we do 1 times 2 plus 2 times 5 plus 3 times half. To get the second entry, we do 1 times 0.8 plus 2 times 0.7 plus 3 times minus 2. Okay, and this is what we'll get. So I'll encourage you to check that what I just said is exactly this formula over here. Okay, so that's matrix multiplication. So let's look at a few special cases of matrix multiplication. So remember that we had scalar matrices. Yeah, so scalar matrices were diagonal matrices in which all the diagonal terms were equal. Okay, so they look like the matrix on the left, C0 0 0 C0 0 0 C. Okay, so let's do this multiplication. Okay, so the first so first of all, is it well defined? So how many rows and columns does this have? This is a 3 by 3 matrix. How many rows does this have? 3. And how many columns does it have? 2. So this is a 3 by 2 matrix. So indeed we can multiply this because the number of columns here is 3, which is the same as the number of rows here. And when you multiply these, you will see that the first entry, for example, the 1/1th entry of this is C times 1 plus 0 times 3 plus 0 times 5. So it's just C times 1, which is C. Okay, the 1/2th entry is C times 2 plus 0 times 4 plus 0 times 6, which is C times 2. So 2 times C. Okay, so you can see what's happening. Each entry of this second matrix, each entry over here is getting multiplied by C. Okay, so I can pull that C out and think of this as scalar multiplication by the constant C. okay, multiplication by the scalar c. Okay, so that's what's special about scalar matrices. So scalar multiplication by a scalar can also be thought of as multiplication by a matrix, namely the scalar matrix of the corresponding size. Okay, so to reiterate what I said, scalar multiplication by C is multiplication by the scalar matrix C times the identity matrix. Okay, in particular, if we put C is 1, right, we get the identity matrix. So from there, what do we get? We get that if you have a, let's say, a 3 by 3 matrix, then if you take the identity matrix of size 3 by 3, again, as I said, identity, you will know from context which identity matrix we are using. So I times A is the same as A, because you can pull out the 1. So nothing is happening. You are not multiplying by anything, meaning you are multiplying by 1. Okay, which is the same as A times I. So I'll encourage you to check these formulae. Okay, and more generally, if you take, instead of 3 by 3, if you take 3 by n, then if you multiply by a 3 by 3 matrix I on the left, you will get A again. Okay, and if you take m by 3 and multiply by I, you will again get A. Okay, again the 3 here is not relevant. You could have used any n instead of 3, but often our examples will be in small size. That's why we have mentioned 3 here. Okay, so there is something special about the identity matrix. That's the point of this bunch of things here. So identity matrix acts like 1. Okay, so when you multiply a number by 1, you get back the same matrix, the same number. The same thing happens with the identity matrix. When you multiply by the identity matrix, you don't change anything, you get back the same matrix. Okay, so identity matrix acts like 1. It behaves like 1. Okay, so finally let's quickly summarize some properties of matrix addition and multiplication. So if you add 3 matrices, it doesn't matter which order you add it in. So this is called associativity. If you multiply 3 matrices, it doesn't matter which two you multiply first, but very importantly, you have to multiply them in the same order. Yeah, you can't change the order. If you do A plus B, then that's the same as B plus A. So you matrix addition is what is called commutative. It doesn't matter which order you add them in. Okay, but it matters how you multiply them. Okay, A times B is in general not going to be equal to B times A. In fact, it may not even make sense to multiply B times A. Why is that? Because the number of A times B means that the number of rows of B is the same as the number of columns of A. On the other hand, B times A means the number of columns of B is the same as the number of rows of A. This may not happen, right? So for example, if you take something like this, and I can multiply by 1, but the other way does not make sense. Okay, this does not make sense. Right, this does not make sense. I hope it's clear. This has 1 column and 3 rows. This has 2 rows and 3 columns. So this doesn't, you can't multiply these two. Okay, so it may not even make sense to multiply them. They may be of, even if you can multiply them, they may end up being of completely different size, and even if the sizes are same, they may not be equal. So I'll encourage you to check such things. Okay, and then some more properties. So if you multiply this by a scalar, yeah, if we have scalar multiplication, remember. So if you do lambda times A plus B, then that is the same as lambda times A plus lambda times B. So this is scalar multiplication. So lambda is a real number. So lambda is a scalar. Okay. Similarly, if you do lambda times AB, then you can first do lambda times A and then multiply that to B, and there will be no problems. It will be the same number, sorry, the same matrix. And in fact, you can go ahead and shift that lambda inside. Okay, so scalars can be shifted inside. Okay, so here you can change lambda to go inside. Okay, so A times B plus C is the same as A times B plus A times C. Okay, and then finally A plus B times C is A times C plus B times C. Okay, so these are identities. How do I check these? So you have to check these based on the rules of addition and multiplication. Okay, so even if you don't formally understand how to check them, um, in given examples, I hope you will be able to actually compute. So I'll suggest that you actually compute things like this. So for example, I'll give you an example here, which I'll suggest that you compute and see what happens. So see if, for example, this is the same as 2 times 1 plus 2 times 3, 4, yeah, and so on. Okay, so let's quickly recall what we have studied today. We have studied what is a matrix. We have studied special matrices, so diagonal, scalar, and the identity matrix. We have studied what is the relationship of a matrix with linear equations, and then we looked at matrix addition. We looked at scalar multiplication of matrices, meaning multiplying a scalar to a matrix, and we looked at multiplying two matrices. Very important, the number of columns of the first matrix must be the same as the number of rows of the second matrix. Only then can we multiply. Okay, and then we looked at some properties of all these operations. Okay, so thank you, and see you in the next video.